Yeah. Actually, I introduced it last year, and I will have a quick look back at some of the slides from last year, and then I will proceed from there. Last year, I already mentioned that large systems are usually programmed, and by programming many objects, and these objects and their interconnections and messages implicitly form a global data structure and algorithms. And this implicit is the problem. We have on the one hand side the objects and the messages, and implicitly global data structures and algorithms. And the debugging is only a local view on the individual objects. And we propose to have an explicit view and a global view on the complete data structure, so that you really know what interactions are there and what happens in the system. And McFSM is a way to have this explicit global view on the objects and their interactions. A short overview over finite state machines and their advantages and disadvantages. Finite state machines do not have any runtime secrets. You can prove everything at compile time, and you do not need to resort to testing because you can really see that's all there is. There is the well-known Chomsky hierarchy, where you have the finite state machines on the one side and the Turing complete machines and languages on the other side. The expressive power goes up when you go from the left to the right, and the provability goes down, and that's the downside. And McFSM tries to go a bit from the left side to the right side, but not too far, just so much that you still have the provability and gain more expressive power. McFSM can handle huge finite state machines. It is thereby extending greatly the range of their applicability, and it retains their advantages. Finite state machines. This is a new slide I'm showing you. These nice pictures are not drawn by me. I have taken it from the internet. And a finite state machine is a very simple thing. You have simple steps between each state. And that is something I have to explain, because if you have a Turing complete program, then you have a state, then some event comes, you do some calculations, you do not know how long this calculation will take, you do not know to which state it will take you, at least you do not know at compile time. The only chance you have with a Turing complete program is to observe its runtime behavior to see to which state it will take you. And I think that is really no good state of affairs, because it is like saying to some developer of a building, you build the building and look afterwards whether it crashes or not. It is, you have to know it beforehand, you have to know it at compile time, you have to know that where each event would take you. So you have to know which is the next state when you get an event in a certain state. And the second thing is you should know how long it takes. So the second feature, maybe I will give another talk another time, because that is something I developed recently and it is still under development. The point is, if you have a finite state machine, as you usually have it, and as I will show you in the DSL later on, that DSL, the domain-specific language I developed, is of course an enhanced TCL language. And if you have something that is developed there, then everything is basically table-driven, and you can just count the steps and estimate what the worst case is. But I also have shown you last year that I have a plug-in interface where you can plug in almost any software and describe with a certain structure what the behavior of this software will be. It behaves like a finite state machine, and there you have to plug in some costs. How much will each step cost at the worst case? And all that enables me to estimate for each step the worst case costs at compile time. So the goal is that the IDE, integrated development environment that I'm developing, can tell you at compile time for every step the worst time costs, so that you know at compile time each step goes like that. And if not, you can dig deeper and improve your code at compile time. It is not as with Turing complete code that you have to wait until runtime and do some tests and oh, that was slow. Let's look why this particular case was slow. No, you get a complete overview of your program. Finite state machines, the McFSM idea explained shortly again. If you look at the clock, you have the seconds, for example. It's 60 seconds from S0 to S59, and you have some external tick event that makes your seconds step further on. And now if you add the minutes, it's another finite state machine. There, the event that triggers the transition between each minute is exactly the transition from S59 to S0. So the transition of one edge, the traversing of one edge, issues an output event, and that may be used by some other finite state machine as an input event. And this is the coupling, that is the basic idea of the McFSM, which stands for multiple coupled finite state machines. To make this work, you need some internal machinery. The XQ is basically a stack. It arises naturally of the requirements. Events must keep their order. Each event runs to completion, and the thing must be lively. That is, you need thread safety and so on. And I will not go into more details with this thing. I just say to make this coupling work, you need some internal machinery, and that is easily done. Now we come to a topic I already indicated, the compile time knowledge. I say the compiler, and by this I mean all the tools you have at compile time, still does not know enough. And the compiler can only assist you with things it knows about. If there's something it doesn't know anything about, it cannot assist you. So what is missing and what should be done? We should make more semantic knowledge available to the compiler. Currently, it knows only what I would call syntactic stuff. It knows about classes and methods and signatures and things like that. It can tell you whether you have written down some method correctly or whether it is available in this method or for this object and so on. But that is really not what I would call semantic knowledge. And we should disentangle the fuzzy Turing blob, which mixes states, data, calculations, decisions, and transitions, and so on. If you have an integer, the compiler knows it's an integer. And he knows you can add something or multiply it or something like that, but it does not know whether this integer is just some data you are collecting, or it is part of the state that, or whether you base decisions on these integers. Like you have a switch where you say case or switch and enum, and you base your decisions on that. And it, what I mentioned before, all the transitions from this state to that state is something the compiler does not know about. It does not know about states, and it does not know about transitions, and it cannot assist you there in any way. The decision structure, that is all the if then else stuff. It is spread out through your code, and it is particularly complicated. If you're thinking about all what you can somehow think is if then else, and all that in your program, it is a very complicated structure. Actually, it is that which deserves the most assistance, and from the point of view of the compiler, it's no structure at all. It's just some if command here, some switch there. That this forms one structure where your decisions in your program are based on. The compiler has no idea about that. Only in the mind of the programmer does this form an invisible structure. And that is very, very bad, because if you have another programmer, you have to teach him that, and he has to make his own picture out of that. It is not something that you have explicitly where you can give it as something I give it to you, and there is the picture of this decision structure. It is, therefore, he must always worry if he's programming, did I forget a case? Or there are so many if this and that, and maybe there is some case I have forgotten. Or do I have some contradicting assumptions? In the one part of the program, maybe just a few lines up, I assume a certain condition holds, and a bit further down, I assume it doesn't. So I have to know which assumptions to rely on in any branch, and there are many more things like that. And all that leads to the thing that we have to rely on testing, and with testing you can never prove that you did not forget a case, or you did forget the case in the testing. So all this and more can be captured with states and transitions, that is with state machines. What we need to do is we need finite state machines that are modular and compile time available, and we need a language that is really expressive and powerful to formulate that, because that is something that was still under development last year. If you have two simple languages to formulate finite state machines, it is really a pain in the you know what. It's not fun to write big finite state machines with a simple language where you really have to list everything. And the major part of this talk will be to show you the DSL I developed and convince you that it is powerful enough. So McFSM is exactly what I said is missing here. McFSM does exactly provide that. Especially here we distinguish between these different kinds of items. We formulate a decision structure and can deal with that at compile time. Now, a short mathematical excursion. It's not very important. I just tell you that you know where to sort this in if you are really doing theoretical computer science. There are Mealy machines. Mealy machines are finite state machines where you have an output. You have actually a function that's usually called delta. That's the transition function where you say, I go from this state to that state if an event in the set sigma is coming. So, and the omega function gives you an output for each of these transitions. McFSM is really the same. It is a Mealy machine, but it has n internal Mealy machines, and these Mealy machines have to be connected. And That's how a McFSM looks like if we look into it. And the tricky bit is the construction of all the delta of the omega of the enclosing McFSM out of all these parts and how to connect them and so on. And the last sentence is the most important. These resulting delta and omega must become total functions. The machinery in between is the stack, as I told you before. And we need a total order for the stack that it works. And this is really what reasoning is about. Actually, it took me a few years to really capture the full power of this sentence. In the beginning, I completely dismissed it. I thought, okay, if you have some case that is missing, it doesn't matter, you just stay in the state you are. But the mathematical answers to all the worries I listed before, did I forget a case? Have I contradicting assumptions? And so on. All that is covered with this simple sentence, delta and omega have to be total functions. And I do not have the time to really explain it in all the detail. It is something one has to think about, and I think it is now, before I go to the next step, to really verify that these functions that we define implicitly with our language are total functions, that can be really, really hard. But fortunately, the IDE is doing it for us. And that is what sets McFSM apart. That is that we have here a tool to do the reasoning and to prove at compile time that no case is forgotten and you have no contradicting assumptions. Now, let's have a look at the DSL code. I did not put that into some, can one see that? Yeah. I hope one can read it. Or should I make it bigger? A little bit. Even more. So that is an input file for the McFSM IDE. And at the beginning, you have something where you can say, this is my package and I'm the author and things like that. Not very interesting. And now what we are showing here is how we might model a traffic junction, where you have traffic lights and you do not want that two lights are red, so are green at the same time, so that people might collide in the middle. So let's begin by modeling a light bulb. So we have a finite state machine class that's called bulb, and before that we have a list called OO with the two strings on and off. And then there comes states, colon, and percentage OO. That percentage thing is one of the things I've invented that are really powerful. Here it will automatically expand the list OO. And the states usually have to be lowercase. I made this states command lenient, so it allows you to write uppercase, and it converts it automatically internally into lower states. Now we have the input events in colon. They start with an I, and we expand again the list OO, so the input events are I on and I off. And the same with the output events. And the output events, there we have two kinds of output events. That is O on, O off, and O is on, is off. And this is on, is off I had to add to make it really a complete function. I have to mention one thing. Currently, my software IDE is not working, so I could not check it really with the computer. I had to look. There might be some hidden bugs because currently my software is not working, but it will probably at the end of the month again. So with the hop command, I define the transitions, the edges of the finite state machine. And now here we have on the star underscore %00. With underscore, when you have on the left side a state underscore state, that's an edge. So on underscore off is an edge from on to off, or off underscore on is from off to on. You see here a star, so I have some pattern matching here. And the pattern matching says is something that is done locally. So the hop command knows at this place we need states that have to match the star. And it looks through the states it has defined here in the states command and tries to fit the pattern. The percentage command is something the hop command does not even see. Because, no, it does see it, sorry. The hop command does see it, but it is expanded before the command executes its arguments. So the hop really first expands all the percentages. And another thing, you see here in this first hop line, there are multiple %00 items, and they are, of course, expanded in sync. That means if on the left-hand side, if the first one is on, then the second one is on and the third one is on. And if the first one is off, then we have I off and O off. And likewise with the second hop command, there I said, because it is in sync, it's the loops. It is something when I traverse from on to on. So it's a loop on the same state. I stay in the same state. And then I output not O on, but O is on. Because now I say, you said I should go to on, but it already is on. So that's the distinction between these two O output events that this bulb is issuing. So let's go further on. I think you have got the first gist about how this language looks like. If we make a McFSM traffic light, we have a list again, red, yellow, green, and the input events are expanded, the output events are expanded, and now I make instances from these bulb class we just had before. I have a red, a yellow, and a green instance, and I have now, because I have instances, I have to specify in which state does this instance start. And if you see here, the one starts in on, the other starts in off state of the bulb. So when this McFSM starts, the red one is on and the other ones are off. Then I connect the input events. There's an I connect, and the one with the slash in front is the input event from the McFSM, from the traffic light where I reside. So we have here an I red, I yellow, I green input event, and these are connected with the local I on and I off events of the bulb. So if the traffic light gets an I red, then this line says this traffic light I red should be connected to the red bulb's I on. And the traffic lights I green and I yellow should be connected to the to this red bulb's off. And likewise, I do it for yellow and green. And then I have here O connects. That's similar to the I connects, where I connect the inputs. There I connect the outputs, where I say my McFSM issues the output O red if the red bulb has issued an output O on. And likewise for yellow and green, and here I do it with is, if it is on. The thing is, I have classes and instances, and now I start connecting the inputs and outputs. And it looks simple now, but I can tell you it was really hard work to come to this simplicity, because I had many solutions before, and they were all very complex. And to have it simple is really the hardest thing that you can think of. Now, let's make a junction out of it. I do not get in all the details because that would take too long. I want to give you an idea how this language is structured and how the finite state machines get connected. But as you already can see with the example we just had, it is every instance of the finite state machines within has some fan out and some fan ins, and that you can prove at compile time that you did not omit a single case, and that from the outputs from the O connects, that there is always one output. That is so powerful, it is really incredible. Because if you have, there comes an input event, and there might be no output. There might be a state combination of all these finite state machines that you have forgotten, and you do not get an output. And that is something I can point at that at compile time. And that is something you do not get with anything else. It is, you have to have a system where the compiler understands what transitions you are making, what is possible, and that you have an omission there, that you forgot something. And without a model that tells you what the transitions are, you have to have it in mind and always hope and worry whether you didn't forget something. Similar it is with the contradictions. With all these connections, it might be that one bulb is issuing an on and the other one too. Oh, 5 minutes left. Oh, okay. I can tell you there's much more to see. I go back to the slides. And jump to the conclusion. No, maybe a little thing I show you again. So that is work in progress as well. I'm trying to model the dining philosophers. There I use the plugin interface where I plug in certain code that is from other that is programmed in another way, but behaves as a finite state machine. I have here the philosophers, they think, eat, or are hungry. And I have a class fork, and then I have the dining philosophers. And what's new here is I have a minus sync in front. So, and I have two kinds of pattern matching. One is with a colon, and the other is with a percentage sign. And the colon thing is really done from the outside, so that I can do things like that here. I can make instances where where the number of instances increases if I change the list here. Currently I have 5 philosophers, but I could just put in here 5, 6, 7, 8, and then it's 8 philosophers. And that's the power behind this language. You just change the lists, and all the connections and all the relations automatically adjust. Yeah. I already cited Antoine de Saint-Exupéry. Perfection is achieved not when there's nothing more to add, but when there's nothing left to take away. And McFSM really concentrates completely on the finite state part. It leaves everything else, all the calculations, all the socket stuff, and so on. It is completely left out. The IDE generates code in different languages. One of them is TCL, of course. The other is C++. So you get a C++ code where you have the finite state machines as you debugged it in the IDE. And then you can put in there any code you like, but you can be sure that all you are doing is correct. You did not miss a case and you have no contradictions. McFSM is simple because it just combines media machines into a compile time decision structure. What you gain is the power of recursive functions in the realm of finite state machines. That is something I explained last year. The simplicity we have of the idea and the system makes a theory produces a theory that allows mathematical proofs. We can do compile time checks, whether we have forgotten any case, that is done automatically, or it will be checked whether there are contradictions, that is done automatically, and you can interactively look at every state and every transition to see whether which assumptions are valid where. We have huge state spaces that get tractable because the state space of the McFSM is the product space of its contained finite state machines. We have a plug-in interface where we can plug in almost any code that it can mimic a finite state machine. We have a lean and powerful DSL. I hope you can see how powerful this combined pattern matching between the percent, that's called extra patterns, and the glob patterns we know from decimal, how this combines to make a very powerful language. And there are further advantages. It stretches from safety critical to multi-core, real-time, and compile time measures. A word to the multi-core. So McFSM is thread safe. So you can fire events from any thread to the McFSM. The McFSM does the transition, and the transition you can assure that it is really fast. You can, at compile time, you can check what is the worst case for my transitions and can ensure it is fast enough. And with this features in place, a McFSM is like a very, very high level mutex. You can say, here I have one structure that captures the decisions of my program, and I can prove that there are no contradictions, and by its thread safety, I do not have to worry about anything with other mutexes and things like that. I just, if I have a calculation that's longer, I put it in another thread. The thread at some time fires the event result achieved back to the McFSM or whatever you would like to have in, and the McFSM takes it just as another event and goes to the next state. And that alone is worth the whole thing, because I know for a fact that there are many companies and people who have big problems with multi-core. Okay. Okay, that's the architecture, and thank you. Any questions?
Don't want to interrupt you.
Yeah, understood. I understand. People are hungry, I understand. Yeah.
Is the code open to the public?
Pardon?
Is the code open to the public?
Not yet, it will be. Actually, that is one future steps. That's the things I already did, and the red ones are the things I want to do. And making it open source is unfortunately not done yet, but will be. It will be coming soon. Tickle soon. That means maybe in the next. You know what I mean? So.
You already use it in practice.
That is one of the things. I had to develop it so far that you can model real life things with it. Currently, the code is not working, but the next step is really to have business partners where I say we use it in this project. And yeah, if I do not succeed with that, it might be that
we get laid off.
Yeah, not so bad, but that the project might not continue in the way it did before, because I'm actually working on this now several years, and I'm really grateful that I could do this work. But the problem is that to find people who have both the understanding that what I'm doing here is really a good thing, and the other thing is the decision power to say we have a project and use it for that. This combination to find is not so easy.
These compilations that you talked about.
Pardon?
The compilations that you have your
Yeah.
description, and then you put it in your application, and at the other end there comes out the C code or the C++.
Actually, that's an old.
How is the runtime? How can you be sure that the runtime generation doesn't explode in a real project?
Actually, the runtime does not explode. What could explode, or the state space explosion I could have in the compilation step. There might be, you might be able to formulate things where this IDE thing says, okay, that is too complicated. Actually, all this is put into SQLite, all the data structures I found, and there you can have some limits where you say, okay, if it's more than 1 million cases, stop. And then I try 1 million cases, and after that I say, sorry, too complicated, and then I show you some of the longest paths I have found so far, and then you can say, okay, this is a path he tries to consider, but it is really long, and you can rearrange your program. So usually I should be able to make a decision, but there are corner cases, and I cannot rule out that you formulate programs that I cannot decide at compile time. But when I decided at the compile time, the resulting runtime is slim, it is fast, and it behaves exactly as you have debugged it. So you do not get the explosions at runtime, you get it at compile time.
This was the question. How do you prevent explosion at compile time, at decision time?
At compile time, it can be really hard. You have to make maybe a thicker machine or more time. But once you have it, you can run it on a small machine, and it goes like that.
So I will stop the discussion now. Who wants to get in more depth in that theme should take a seat next to Florian at lunchtime. We should now go to lunch. Otherwise, they may.
Okay.